بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله. خلينا بس ننتظر كمان دقيقة أو دقيقتين to make sure all audience attendance. ملاحظات بس في السريع إن شاء الله. حطلع على questions من الحضور في نهاية الworkshop. Please feel free to write your questions in the applications الهوفا. كمان عملنا بول أو question كانت بخصوص المين بارير أو العوائق أو الchallenges اللي بتواجه الداتا ساينس community من نقل الكمبيوتيشن أو الداتا analytics from centralized architectures مثل الكلاود كومبيوتينج إلى more decentralized architectures مثل الإدج كومبيوتينج والIoT. ففي عنا تقريبا 72 replies بس. حنتظر نعرض نتائج البول ونعمل discussion حولها في نهاية السيشن إن شاء الله. meanwhile مثل ما حكيت لكم feel free to send your questions وإن شاء الله في نهاية السيشن بناخذهم واحد وبنفتح discussion بخصوصهم. تمام. إذن بسم الله الرحمن الرحيم. أنا الدكتور فراس عوايشة، حاليا lecturer في البيج داتا سيستمز جامعة تارتو في استونيا في أوروبا في الدلتا ريسيرش سنتر and تارتو يونيفرسيتي. اليوم رايحين نتحدث عن الداتا برايفسي في البيج داتا and edge intelligence era. فرايحين نتحدث mainly from my perspective as a data engineer about data privacy in big data. And big data can be largely distributed systems like an IoT or edge computing, and it can be more centralized like running big data applications and frameworks over centralized architectures such as cloud computing. نشوف الأجندة وقبليها مثل ما أسلفت I hold PhD من إسبانيا في جامعة سانتياغو دي كومبوستيلا ثيتوس ريسيرش سنتر وماستر degree from New York University United States. I'm a big data engineering and data privacy researcher and architecture. Before my current position, I work as an adjunct lecturer at Charles Darwin University, Australia, and postdoc researcher in Edinburgh Parallel Computer Center في Edinburgh University, Scotland. So today we will start a brief introduction about the big data era and different architecture deployment models. We will talk about the edge intelligence paradigm, and as the name indicates, هو adding more AI to the edge of the network. رايحين نتحدث بعديها عن data privacy issues and challenges, which is a leading concern among practitioners. A set of solutions to mitigate and to control such concerns will be discussed and proposed, among of which will be federated learning. So today's talk is about data science and data engineering, and one of data science powerful tools is machine learning. And for a long time, machine learning was mainly depending on centralized architectures, like allocating all your data in one repository. It's considered a cloud repository, and run your algorithm over these data. But recent and modern requirements and applications required more distributed architectures. So how can we run machine learning algorithms and applications distributedly is the federated learning backbone, and it's a way of running a distributed machine learning with privacy by design in back in mind. So the architectures and those who start proposed federated learning, they propose it from first place to be to maintain privacy. So it is a privacy by design. It was designed to be to maintain privacy of data. بعديها حنتحدث عن associated technologies, وممكن برضو I will add more big data security frameworks of centralized architectures. So let's say that this talk will be distributed over two logical parts. First one, we will discuss the IoT and edge architecture security, which is decentralized architecture. Then we will talk a little bit about more centralized architectures like cloud computing. I will discuss some opportunities and open challenges for further research. And inshallah, we will conclude this workshop. Okay. So, how big is our data? And let me start by defining big data. So one will assume that we can define a threshold that define a big data application. For instance, if we have zettabyte of data, we will call it big data, and I would say not necessarily. To start with, I always say that if traditional processing way become low performance with low latency, and you need to accelerate your feedbacks and your outputs, and traditional ways like traditional databases, traditional batch queue systems can't maintain your requirement, then you need to pick up a solution from the big data realm. And maybe the big data as an era had started early 2000s by the phenomena of the Hadoop stack. So for the first decade of the 2000s, the terms big data and Hadoop computing were tightly coupled, and Hadoop has grown to become not a big data processing engine, but a big data stack of tools and open source frameworks for processing, storing, orchestration, visualization, and many other services over big data for big data practitioners and clients. So big data and large-scale data analytics are giant and fast-growing data processing engines. We are producing and allocating more than ever data. If you look at the figure in the right, it represents how many data we allocate in 2020 in a minute. So you can see that we're allocating and collecting a massive amount of data every 60 seconds, and maybe in currently data allocation patterns, in one day we allocate more data than a whole year back in the 90s. So different types of deployment architectures with various network models rather than the centralized model has been proposed. As I said, big data has a very strong relationship with cloud computing, and mainly motivated by the scalability and pay-per-use features that the cloud can provide. However, applying big data applications can be deployed over different architectures. high performance computing and supercomputing, for instance, which nowadays become known as high performance data analytics, is a way. Running big data applications over grid computing and IoT architectures is another way. So allocating massive amount of data over centralized system is the dominant model. Like if you want to run an AI application, a machine learning application, any different processing model of big data application like micro stream processing with Apache Spark, or batch queuing with MapReduce. Usually we will use centralized system like cloud computing. This is mainly because they represent a reliable resource and communication where you can maintain the security and privacy and control more the security surface and the vulnerability surface, since you allocate all your data in one centralized repository, where you can have more resources to implement more complicated processes like encryption, etc. However, like modern requirements had introduced Internet of Things and Internet of Everything, which is a giant and fast-growing data generating engine. Like in 2020, the number of smart sensors, actors at the edge of the network become a very massive computational architecture that one can't simply deny or ignore. So currently the estimations that we have more than 50 billion device and smart device at the edge of the network, ranging from mobile phones to laptops, across like sensors and actors. They could have some computational capacities or not, but still they are massively distributed and have some power. Many modern applications require high latency with almost real-time response. So keep allocating the data from the edge of the network and send them to a centralized architecture can come back with a latency. There's a golden rule in big data, which is try to keep your data local and minimum transfer your data only when it's required. And this was like moving data from server to server or from node to node, not particularly for IoT. But this particular rule is still applied in IoT. Imagine that you have a smartphone and you're running your text, your type on your smartphone. So you want to have a recommendation system that give you recommended words, for instance, if you have a typo or something. So if we want to keep learn this hybrid like natural language processing and machine learning application in the cloud, this can come back with a time latency. Or try to imagine a modern connected vehicle, a cloud of vehicles like smart vehicles. If we want to keep all the process in the cloud, that definitely will come back with a latency. So some modern application require real time and locally processing your data. So a meeting point between IoT and big data application is inevitable. Like IoT is nearly helpless without fast, powerful analytics that enable the best decision in real time, while big data strength become more pronounced in the presence of lot and massive data that are diverse, noisy, and multidimensional, which is what IoT generate. So growing and success in one area will promote growth and success in the other area. They are very extremely tightly coupled. To understand more what we represent today and how things are worked, if we check this abstracted architecture in the right that represent the IoT edge to cloud, to more centralized and to the edge of the network, even that it is very abstracted, yet it can represent the theory behind what we are talking today. So IoT to cloud data pipelines and in general offloading and retuning IoT to cloud is expecting to lead the modern of big data applications, realizing the smart everything vision. If we want to have intelligent transportation system or smart homes or smart cities, a tightly coupled IoT to cloud is one of the main solutions. So edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed, like where you allocate your data, you process your data. The main features. Okay, now I got the two screens. So the main features and the main future directions is connecting everything and everyone at any time. It is highly dependent on fast and smart analytics. People will become less involved in decision making over time. After all, it is an AI era. Of course, there will be still a man in the loop controlling the process, but we involve AI in our decision making more and more. And it's estimated that up to 40% of IT application would rely on local data analytics in the near 5 years, in the near future, 5 years, edge, fog, and IoT. So traditional cloud computing cannot meet the needs of people in the era of AI efficiency, and we need edge intelligence to come into being. Like the previous way was edge computing, allocating data and send it to the cloud where you can apply your AI applications and algorithms. Nowadays, we want to bring the AI closer to the edge of the network, and this trend has become nowadays called edge intelligence. Okay, so the edge computing can be characterized based on its geographical distributed. So it is massively and large-scale distributed architecture. It is autonomous and smart, and we will understand later on what we mean exactly by smart. It is scalable, and in fact it is elastic, like it can be scalable horizontally, adding more resources to your architecture, and it is real-time interaction, or at least it is more preferable as much as it could be real-time. And of course, heterogeneity of the architecture. In more centralized models like a cloud, you can set your cluster to be homogeneous. But in an IoT and edge architecture, the heterogeneity is very, very huge. Like the amount of data in each point can be diverse. You can have more data in one node than the other, and the capacity, storage and computation in one node can be more than the other. So the goal is to unleash services, mainly data analytics, to the network edge, since the edge is closer to user than the cloud. So edge computing is expected to solve many of these issues. And artificial intelligence of things is another way to say intelligent edge or edge intelligence. So edge intelligence is expected to push AI computation from the cloud to the edge, enabling distributed, low latency, and reliable intelligent service that in the best case can match the centralized, or the goal is to match the centralized architectures. On the other hand, intelligent edge aim to incorporate AI into the edge for dynamic and adaptive edge maintenance and management. So edge intelligence or intelligent edge, and is there a difference between these two terms? In fact, there's might be a slightly different, like in edge intelligence, we mean that AI application runs at the edge, while intelligent edge, we mean that the edge itself becomes smart and autonomous and self-controlled environment. So machine learning AI for optimizing the edge, for instance, like scheduling at the edge become smart and automated. This is an example which resort to distributed learning for maintaining and managing multiple aspects of edge computing, like controlling network, like edge caching and computation, offloading, communication, and extra. So while edge intelligence AI addresses that data transmission bottleneck, instead of keep transferring the data to the cloud, which came back with more latency in terms of time. Yet it has some limitation and challenges. Edge has limiting computation and storage capacities compared to the cloud cluster. Electricity latency, like not all the devices can be connected to reliable electricity plug-in. For instance, in your mobile phone, if you want to keep your CPU fully utilized for running some machine learning applications, maybe in 1-2 hours battery will be dead. So electricity consumption is another concern. Also, it raises in new security and privacy as well concerns. Untrusted participants to your architecture, distributed geographic multi-source of data that can become a vulnerability, and different layers of the network, like you're dealing with IoT, edge, fog, cloud, and protocols like HTTP and MQTT can be involved. So the security surface is very big in such environment. So edge computing causes tremendous exchange of data, bring more privacy challenges. Like, as I said, we try to keep data movement to minimum. So decentralized, liable, and privacy by design frameworks are required more than ever. And by privacy by design and security by design, I mean that your solution, your architecture, your framework has been designed in the first stages to be secure and privacy, not try to propose a solution and add security to it later on. We have to make sure that security and privacy have been considered and think about at the early stages of your design phase. And speaking about data privacy in this realm, edge computing can potentially receive large amount of privacy sensitive data. Try to imagine, like, for instance, a country that have a smart ID or healthcare system or bank system that relies on edge processing. So these data can be labeled as sensitive. Edge computing have limited resources, as we said, so they can't support complex security mechanisms like multi-layer of encryption and wire encryption and access controls using like attribute-based or any other type of identification and access control. So all of these mechanisms required some resources, some computation, and accordingly some time. And as we said, one of the strength points of edge computing is time latency. So encryption on wire and at rest and blockchain technology and access control are utilized, as I said. Yet again, so this will add more system complexity. It is resource intensive, computation and power, and time consuming. So we need to come up with new solution that brings privacy and security to our data while maintain processing at the edge of the network. So a novel data analytic setting that is largely distributed, highly private and high accurate is required now more than ever. In the data form an edge node is leaked, the consequences can be serious. So this is something that we have to consider. So federated learning, as term, is born. And as I said, federated learning is a type of distributed machine learning. So it addresses the previous concerns. And by definition, federated learning is a machine learning technique that trains an algorithm across multiple decentralized edge devices or servers holding local data samples without exchanging them. So you keep your data locally, you don't exchange your data, and you run the same model across these distributed nodes, and in somehow you can make other nodes participating in the architecture or in the system learn from each other, and we will see how that can be done. So federated learning enables multiple actors to build a common and robust yet a distributed machine learning model without sharing the data. This allows to address critical issues such as data privacy, security, and data access right, and access to heterogeneous data that the edge network can provide. So in this architecture is non-independent and identically distributed data across devices. So the heterogeneity, this indicates the heterogeneity of the data in the nodes. So taking the main feature of a federated learning by checking this small figure here, we have different edge nodes with a central server that will keep orchestration of the process. So the server will choose a model to be trained, and the server will send this model, this initial model, to the nodes, like this dash represents the model. These nodes will use their local data, the allocated data at this node, to train this model. So the train will be distributed among these nodes with the same model using different data. So this can have more data than this one, and this one can have less than the other two, yet it only trains on its local data. Later on, these nodes will send to the aggregation layer a common aspect, like for instance the weight of the model. The weight of your model can be sent to the server, where aggregation like averaging can take a place, and we will send back the updated weight to the edge of the node. So this process is represent an iterative learning, like relies on iterative processing broken up into an atomic set of client server that include like reinforcement learning, online learning, etc. And non-IDD data, where like attributes QE and labels QE, like non-overlapping attribute and partially overlapping attributes QE can take a place or happen. So in federated learning and in terms of architecture, we have two like main trends. One of them is called cross devices federated learning, and the other is cross silos federated learning. So in cross devices, the number of participants or the end nodes is massive. Like imagine mobile phone or a mobile phone cluster or edge architecture, where the number of participants can be massive, while there's small data set per party, could be the size 1 mega, 1 giga, whatever a mobile phone can allocate locally. It is less limited availability and reliability. It can go down at any point. So this is one of the drawbacks. And some party may be malicious, like since we're talking to thousands, 100,000, and maybe more participants. So some of them could behave maliciously, and this is more vulnerable. The other architecture is cross silos, where the number of participants can be much less, like in hundreds, tens to hundreds. A good examples of this can be a healthcare system in a country. Like the Ministry of Health is the centralized party that keep track different hospitals. Another example can be a company that have the head branch and different distributed branches, like a bank, for instance, with different branches. So number of participants and parties and end nodes can be less, and it could allocate medium to large or massively large data sets per each party. It is more reliable and almost always available, since it's more controlled environment, and parties can typically honest, but again, this is not 100% guarantee. At least from security perspective, you can't say that it is fully controlled and secure. So, let's see how a typical federated learning algorithm would run on before we dive insights into the algorithm and the equations of such a model. So as we said, we have several edge nodes at the end of the network. They collect data locally, like they don't share data at all, only the data that this device or this party have. The centralized model, the server, will choose a model to be learned, and each party make an update using this model. So the server will choose the model, and it will send this model to the parties, to the end nodes. Next, the end node will run this algorithm, this model, or like for instance machine learning. It will start the learning process. It will send the updates, for instance, as I said, the weight of this model back to the server. So parties share local updates for aggregation based on the learning process that it had at a time. So we will send the weight of the model to the server to be aggregated. For instance, average can be done. Now, since we allocate all weight from all end nodes and we make an average, we have more accurate weight that can be sent back to these end nodes. So the end nodes didn't send the data; they only sent the weight of the model, and averaging had taken place in the server and sent back to the edge node. So server aggregate updates and sent back to parties. What happens now is that we have more accurate model at the edge of the end node, and we can run an incremental or iterated approach, like keep running till we reach like almost a centralized performance model. So this can be it is the rule of the man in the middle: how many rounds of aggregation and how many iterate rounds can be run at the edge of the network. So as you see, it is like an IoT to cloud. Like you can keep the server in the cloud, or it could be even in the fog, like in an environment more reliable, more trustable, have more computational capacities, maybe plugged into the electricity, for instance. But as you can see, this can represent like a bottleneck or a single point of failure, and the community had addressed alternative options. And back to the federated learning architectures, we say that there's the server orchestrated federated learning, where each nodes communicate with the server, and there's a global coordination or orchestration and aggregation level, which could be in the cloud using a server. Server, as we said, is a single point of failure. So there's also a fully decentralized federated learning. Think about it as blockchain. Like there's no server that keep allocate and aggregate the updates, yet all the edge nodes are peer-to-peer, and device-to-device communications take place where no global coordination or local aggregation can be found, yet you share the weight of your model among your peers, and they will make the average with more iterative and more incremental way, and at the end we can reach the same goal, which is more accurate model. Naturally scale to large number of devices, so this can be implemented more to the cross devices than the cross silos architecture. Great. So as you can see, even that it is a new trend, like federated learning have been proposed 2016, yet it's gained the community attention, and an actual work had started like 2018. So the number of papers in 2018 was about 100 papers only in federated learning the whole year, while in the first quarter of 2020 there was more than 300 to 400 papers. So we're talking about more than 1,000 to 1,500 in 2020 compared to 100 papers in 2018. And 2021, it is extremely hard to keep track with all updates and advances in this trend. It include networking advancement, communication advancement, aggregation algorithms, end node scheduling, and much more. So it is hard to keep tracking and to keep up with all the development. Yet it's worth to study, at least in an abstracted way, the federated learning as as an expert in big data, I can say that federated learning is becoming a booming solution, and it gained much momentum. So we're now talking about, after we talked about the architecture of this solution, a very key component is the aggregation of layer of this, or aggregation process of this solution. So one of the most common way is FedAVG, or federated average algorithm. And it would be useful for everyone to go now in a more detail and look at the concrete algorithm behind FedAVG. But first, I'll define some basic notations. For more formally, we will consider a set of key parties or clients, where each party K hold a dataset, day key, or K, sorry, which is made of NK points, and the number of data points is not necessarily the same across all parties. One can have more than another, as we said earlier. This is part of the heterogeneity of the federated learning in practice and in principle. So I will donate by D that joins all the local datasets, make it the joint dataset, which will never be put in a central place, but this is just denote the full data, and N to be the total number of data points, and we sum this size of all data sets, like summation function. So and what we will do over here is we focus on the problems that can be written in the form of minimizing an object function that depends on the data as some parameters, theta. That here we assuming in RP. So theta represents the model parameters, or in another way, the weight of the logistic regression, or the weight of deep neural network, something like that. And hence can be applied to various models. So this abstracts the problem by writing as the weighted sum of the local cost function. And the function fk is the sum over all fk's, which is the local cost function of party k or client k, and depends only on that set dk, the associated dk, that set of this party. This is weighted by the size of that set and the local cost fk, the sum of some cost on each of its data points. And lastly, this is in general, and generally speaking, covers a broadcast of machine learning problems, but not all of them. So if you put everything together, and if you collect the pieces, you get the average cost on each data point, where in this case each data point give the same weight no matter which party got from. And this is maybe an open challenge that we can discuss it later, like if we can prioritize or ranking the nodes contribution, like when you have more data, your algorithm can be more accurate, etc., than treating them all equally. So moving on to the concrete algorithm, and now we got the notations, and let's move on to the as I said, algorithm that represent the FedAVG piece of code. which is very commonly used algorithm, which is also in the community called local SGD. SGD is the same FedAVG algorithm. They are the same. Find it very simple idea behind this algorithm. So we are seeing what in the left algorithm, what's happening in the server side, and we will assume for now a server orchestration setup, not a peer-to-peer or fully decentralized architecture. The algorithm parameters are client sampling rates, and it goes like this. The server initialize the parameters of the model to some theta. At each round, it will select randomly a subset of clients, basically a proportion row of the k client, and you can basically select everyone, and then it will ask each of these selected clients or party a model update. So server allocate all updates and perform a weighted average of the model updates by clients. And we can see the client work on the right algorithm, which is in the client side. It will run like e-rounds, and you can control e-round how many rounds you want to run, making some learning rate, and then send the updated parameters to the server. So when the round set to be 1, it is equivalent to classical parallel SGD or FedAVG. While when you increase the number of these round, each client perform a multi-local SGD setup, like incremental learning, and before communicating with the server. Right. So some applications, if this architecture had grabbed your attention. So scalability of algorithm to large number of parties, like mobile phones and IoT, smart homes, smart health, smart electricity, maybe even defense industries and industry IoT in general. Like, it can serve a very broad spectrum of applications. Federated learning techniques and its applications, as I said, in healthcare. For instance, if you want to train your model for cancer detect, and still you don't want to share your patient photos and data, so you can train your model locally in the hospital, send the weight of this model to a centralized that aggregate the whole data, the whole weights from all hospitals, and update your local model for more accurate application. Also, federated learning and its application for recommender systems and natural language processes, as I said, in your mobile phone while you are tapping or recommending some advertisement, etc. Federated learning and its application in smart transportation, obviously intelligent transportation systems, Internet of Vehicles, connected vehicles, and cloud of vehicles are one of the most beneficial application of such a solution. Like, try to train your vehicle locally and aggregate all the weight and update your model. Also, as I said, in industrial IoT and in energy prediction, in smart energy, smart homes, smart cities, you name it. Let me just capture my breath a minute. Okay, so after we saw how federated learning can be privacy by design, in the first place, it didn't send data of your local data to any other party or client. So it maintained data locally. So this is privacy by design. But now what we will look at is associated technologies that came with the big data realm. Like if you look at the general view of big data, we almost touch the top of this realm in terms of infrastructure, different different service providers like Cloudera, Hotel Networks, and Amazon Clouds are server providers. Different analytical stage can take place, like visualization, machine learning, AI, and you can run several frameworks ranging from Spark to MapReduce to data streaming with the Storm and Flink, and NoSQL databases like Cassandra, CoachDB, MongoDB. So it is a very wide spectrum of applications, of tools, of layers, like running business intelligence on top of processing and post-processing stages. So now I will give like also a brief background about data privacy in the general big data in a centralized way. So big data security and privacy can be characterized mainly by provide easy of use mechanisms at scale. Like scalability is a very important aspect in big data. In centralized architectures, you can scale vertically and horizontally, like add more nodes to your cluster or add more capacities and resources to your node. So another characterization is dynamic and lightweight and distributed. So your solution or your cluster has to be dynamic, the solution has to be lightweight, and it have to consider distribution and parallel computing. Flexible of adapting to client requirements and demands, and federated learning in the first place came from the client demands. From an architecture viewpoint, big data is characterized by system interoperability, interaction among various security frameworks and mechanisms. Also model usability by any big data system, not a TS system. Service performance, security must deliver in functionals in a real-time fashion for data stream and real-time processing frameworks, and opens and extensibility to maintain integration of new frameworks and mechanisms. Most of the big data frameworks, if you're looking from Hadoop to Spark to NoSQL application like Cassandra, Mongo, to data stream with Flink or Storm, all of them are open sources. So to keep integration with this stack of solutions is a mandatory. It is something that you have to do. It is not you can't build silos around your framework and application. Another associated technologies, and in this figure I describe an abstracted layers of an overall data security layer architecture. So it starts from the bottom up to top. So consider a cloud computing, like I call it big cloud, like running big data over cloud computing. We simply call it big cloud. Imagine a big cloud architecture where you need at first to gain an access to that system, and we will discuss in the next slides each layer in details. So access control that include authentication and authorization, integrity while transferring data, governance over data and metadata of the process of processing stage, availability, so it is more related to trustworthy environment, but availability and lifecycle management, and on top of that, confidentiality, like using encryption with different approaches. Auditing and orchestration are cross layers, like you keep auditing after each layer, and orchestration, of course. Here I put some open source from the big data stack frameworks, Apache Ranger, Apache Knox, and Sentry. So Sentry and Rangers are very similar. They are authorization mechanisms or frameworks, while Apache Knox is an authentication framework. Think about it as the primitives or the gateway protector. Like if you want to gain an access, for instance, to Hadoop cluster from an external client, you can at first log in for authentication at Knox. At Ranger, the administration can set policies, rule-based policies, for instance, about that client, what authorization does he have over the cluster. So access control, wire encryption, at-rest encryption, auditing, and evaluation and penetration testing. We will discuss all those. In physical and infrastructure protection, which is an access control, in fact, it involves the core facilities and of sensors, storage, and network. The other layer is logical access control, which represented by authentication and authorization, refers to a set of rules and procedures that control access to cloud, connect, and data. It can be subdivided into authentication, authorization at multi-layers. For instance, the LDAP based and Kerberos protocols, dual stages authentications at mesh network and the edge of edge layer, to name some examples of authentication. Wire encryption is a third integration layer, integrity layer. So it enforces end-to-end protection of all communication among nodes. That could be in the edge nodes, from edge to cloud, encryption end-to-end, and even internally in the servers, in the cluster, if it is composed of different servers, also maintaining end-to-end encryption, and of course SSL and TLS protocols and encryption can be used. For at-rest encryption, most big data frameworks like Hadoop use transparent data encryption, data at halt protection, or data at rest encryption. So as a security tool, it fortifies data confidentiality by ensuring that an authorized entity can only access the system using traditional encryption tools or multi-layer encryption. Transparent, as I said, data encryption, blockchain of things, and identity-based encryption and attribute-based encryption are other examples. But in Hadoop, at least in Hadoop environment, you can set a transparent data encryption over the whole file. You know, the backend storage is HDFS, or the Hadoop distributed file system, and by using TDE or transparent data encryption, you encrypt the whole file path. So if you encrypt a file, all its children or dependencies will be encrypted as well. Next stage is editing and analysis. Refines editing, governance, and compliance control. So compliance is to verifying the commitment of service provider to follow specific legal requirements and standards like smart contracts and policies that can be set by administration with hearing the client's requirement. Editing is a subcategory of analysis. It could be where any secure model should not only secure its entities but should perform security auditing. For instance, keep auditing over log files for access control when each client had logged what he did and etc. information. To perform security auditing at the whole service layers from sensors to the cloud. Evaluation and penetration testing is a control element that shapes the policies and the practices, in fact, and procedures. And hence it reflects to responsibilities of the service provider. So it is a tool that provided by the service provider mainly. What open challenges that facing the community now? It is a very broad challenges, but to narrow a bit and name some. Scalability of algorithms to large number of parties like mobiles, IoT, sensors, wearable sensors, etc. is extremely hard to keep. You need a very robust access control to start with, and it has to be. It has to not affect the performance of your application. Like the security layer has to be a very time intensive procedure. At the end of the day, we're talking about data on stream and real-time application, so it has to be lightweight. And it has to take full advantage of privacy amplification schemes. So design more tolerated, possibly relaxed notation of privacy with generic mechanisms. And one example, one prominent example these days is the blockchain technology. Unfortunately, there's no enough time to describe the whole background of blockchain, and maybe it's not the main focus of this talk. Yet I'm sure that other keynotes will talk definitely about blockchain, and I'll be personally looking to that as any security practitioners these days have to. So another challenge is match formal privacy guarantees with initiative notation of privacy for a given application and relation with legal definitions. And lastly, dealing with the collusion and malicious behavior of the large-scale distributed system or large-scale data analytics system we're dealing with. So in today's session, a high-level, I consider a discussion has been proposed to address the big data, this is a typo, the big data security demands for the big data and edge intelligence realm. At least I hope that you have more knowledge about what we mean by edge intelligence and a brilliant application of this run, the federated learning. Also today, a privacy-preserving machine learning and federated learning application has been presented, which is booming topic in the core machine learning community, but also in applied fields like in the industry, IoT, healthcare, and we name other applications of federated learning. There are many current research interests and open challenges to investigate from different layers, from communication, networking, to more sophisticated federated learning algorithms, averaging approaches and methodologies, and applications. Try to use these federated learning applications. And one thing maybe I forget to include in my slides is to name some open source federated learning repositories on GitHub. So please, if anyone interested in federated learning and data privacy in general in edge intelligence, send me in the last slide I have my email, and I will be happy to name some open source repositories and frameworks, and I would be happy to discuss further collaborations. To name some, there's Fiden, PyTorch distributed, Flower, and I already said Fiden. So there are a few, actually more than a dozen of open source frameworks, and all of them are published as an open source. So, as I said, get in touch if you're interested in federated learning, edge intelligence, and big data deployment architectures and securities. Thank you for your listening. I will check on my tablet if we got any questions from the audience. Maybe it's time to send me your feedback. Here you can see my email, Feras Awaysheh @ut.ee, and this is my webpage. I'm currently working at Delta Research Center, a beautiful smart building. You can see it here in the photos, and I'll be happy to hear your feedback. I include also some few references, all published 2021 by me. Big data resource management and networks taxonomy survey and future directions, active machine learning adversarial attack detection in the user feedback process, also security by design for big data frameworks over cloud computing, and trust evaluation vehicular cloud. It's a trustworthy evaluation framework for industrial connected vehicles in the cloud. And lastly, big data security frameworks meet the intelligent transportation system trust challenges. So thank you once more, and I have 3 questions. So one question, unfortunately, I don't see the names of the questions, so I will read those questions. 1, are there any open source implementations for the federated learning? And I believe that we discussed that. Yes, there are many federated learning open source repositories on GitHub. I'll be happy to share a list of them. We're currently running 4 to 5 of them on our private cloud. So I have some hands-on experience with those. Feel free to reach out, and I will send a list of those. Second question, as 5G speed is data transmission in real time, and how it can help on the big data to be mainly allocated on the cloud, breaking the golden rule. Very interesting, very good question. So you said how 5G, and I will say beyond 5G, you have to keep in mind that we came from academia, so we're leading not the current processing patterns, but mainly we're proposing what will be happening in the next 5 to 10 years. So the current discussion is about beyond 5G and how we can fully explore the 5G potential and the 6G communication system and transmissions. So the question was how 5G will affect the transmission from IoT to cloud. And I would say the following. Imagine how 5G and beyond 5G communication can affect the edge itself, like two vehicles coming across each other and communicate about traffic, for instance, about an accident ahead or etc. So the beyond 5G communication is still very worthy and very interesting, even in the edge layer. Of course, IoT to cloud using beyond 5G networking and communication will facilitate much, yet even at the edge layer in the wireless sensor networks, in the mesh networking like SDN, NVF and slicing, the virtualized networking layer, 5G and beyond 5G is another hot topic to be discussed. So unfortunately, I see that the third question has been deleted. Maybe we had addressed it while we was talking. So I believe that we don't have any further questions. So I will go on to the question that I asked in the beginning of this talk and the poll of my session, and we had 88 responses. So the question was, what is the key challenge of data analytics for moving computation from the cloud to the network's edge, where data is allocated in an IoT? So the question was, what is the main challenging that doesn't make the practitioners sending or making data analytics at the edge of the network? So 51 out of the 88 replies was security concern, 13 was performance degradation, and this is not very straightforward. So for that streaming and real-time applications, edge analytics is very useful. Yet it can become a bottleneck, like, because as I said, we have less resources in the edge of the network. So as a designer or as a data engineer or as a data architecture, you have to pick your solution, the tools of bag of tasks. Either your application running small jobs, but they are massively distributed, so edge computing can be useful, or you need a fewer number of tasks over greater data set, a massive data set, where cloud computing can be better for you. So performance degradation is both sides. The third option was system complexity, which is still true, yet with the advances in infrastructure as a code, serverless applications and architectures, and functional programming. So system complexity, and maybe in one of my slides I said that development in one area in computing can serve others. So development in large-scale distributed system processing and microservices and serverless architectures will help to facilitate edge processing, so which maintain the complexity as well. And there's the fourth question option was other, and 6 out of 91 says that it could be others. So I can say that 60%, 60% of the replies was security concerns, and that is in fact true. You can't send your application to be run in edge nodes without having security as a main concern. And in this brief session, we saw how we as a big data community try to handle and to address this problem. One way is making a distributed machine learning without sharing the data. This will maintain your data. Yet what about man-in-the-middle attacks? Like one can sabotage the server. Or what about malicious clients that send false weight of the model? So yeah, there still be some open challenges, and it's our role as researchers, as cybersecurity and privacy to come up and address these concerns. So I will wait another couple of minutes to see if you have any other question. I'm updating my session QA. Okay, I think that this concludes this session. Thank you for your patience and for listening. I always prefer face-to-face and at least interactive sessions. Yet I'm very happy that we had did this, and feel free to send me your feedback on the email. I'd be happy to discuss collaborations. Thank you, everyone. السلام عليكم ورحمة الله.